All right. Hello and welcome to my presentation. My name is SethTribbey. I'm the Vice President of Sales at Solspec. Really excited to be presenting at EnerGIS 2021. A conference I've participated in several times throughout the years, and really excited to be to have the opportunity to present again today. My talk is on distributed cloud infrastructure and machine learning applications in remote sensing, particularly focused on pipeline integrity management. Thought for the agenda, just kind of go through maybe a quick introduction to the company, Solspec, who we are and what we do, talk a little bit about the evolution that we're seeing in pipeline integrity management, as well as the kind of evolution of remote sensing technology that's available to address some of those issues that have come up. Hopefully we'll have time for a quick demo and share a customer success story, and then of course take any questions that anybody has at the end. So Solspec. So the company I work for is called Solspec. We're a remote sensing company based in Denver, Colorado. And I would describe our areas of expertise as falling into three primary categories. So first of all, expertise in remote sensing. My entire background is in remote sensing. The CEO's entire background is in remote sensing. So a lot of experience there. As well as earth science applications of remotely sensed data. So we do a lot with hydrology, geomorphology, soil science, landscape ecology, things like that. But a big part of what differentiates us from a lot of the other remote sensing and analysis firms that are out there is that we do all of that on top of a high performance computing and machine learning backbone. And really how that translates into value for our customers is that we're extremely focused on streamlining the remote sensing value chain. So, if you think about what it takes to get value out of remotely sensed data, of course you have to acquire it, whether that's with drones or with a fixed wing aircraft or from satellite. But then there's quite a bit of effort that has to be put into processing that data into a data set that's actually usable. So, for example, taking multiple SAR images and then producing an interferogram, or taking raw waveform LiDAR and processing that into a point cloud or a digital terrain model. So we've actually written a cloud-based LiDAR processing engine that enables us to process LiDAR at a fraction of the time and cost that traditional LiDAR providers can. But on top of that, once you get that baseline data set, you typically then need to analyze that data to relate it back to the problems that you're trying to solve. So we've built a series of automated analytics, some of them leveraging machine learning to relate that data back to the problems that our customers solve. We also host, manage, and serve that data for our customers. So, remote sensing data is of course raster data, requires a lot of processing and management to be able to distribute that throughout your organization. So we remove that burden for our customers by providing streaming services as well as a 3D web visualization platform. So, if you think about kind of the traditional approach for collecting a lot of these data sets, it might take a day or two to fly your data, but, the conventional LiDAR providers or remote sensing providers may not actually deliver that data to you for another 2 or 3 months. And even then it's kind of like, hey, here's a 300 terabyte hard drive. Thank you for your business. Best of luck with your analysis. We can process data at a fraction of the amount of time other providers can. We've written automated analytics that relate it to the problem you're trying to solve. We host, manage, analyze, and serve that data to you, as well as providing a visualization platform. So really what we're trying to do is take this really, really big, complex data and streamline it into decisions that provide business value and we do it fast, and we do it at a really good price. So talking a little bit about one of the big problems that we help solve, particularly in Appalachia, in the Appalachian region. So, you know, if you think about the traditional approach to pipeline integrity management, it's traditionally been very focused on the pipeline itself. So how is the pipeline designed? How is it built? What kind of material is it made out of? What's its expected life? You know, a lot of maintenance and inspection data is coming from the inside of the pipeline out. So, you know, pigging and digging, you know, ILI tools, bend, strain analysis, things like that. And then kind of combining all of that data to look at the probability of failure, consequence of failure, those sorts of things. And what data is telling our customers and really kind of the pipeline industry as a whole is that a lot of pipelines are failing in recent years, not due to a failure of the pipeline itself, rather they're being caused by threats that are coming from the environment that the pipeline operates in. So things like geohazards, like landslides and land movement, erosion issues, hydrology issues, seismic issues, flooding and inundation, third-party encroachment, things like that. So we built a program that we call right-of-way integrity management, where we go out and we collect remotely sensed data, process it really, really quickly and at a really great price. And we built all of these automated analytics to kind of give you an above-line inspection to help you identify, prioritize, and monitor a lot of those issues. And so if you think, in addition to kind of this evolution that we're seeing where a lot of these pipeline operators are focused on trying to understand these environmental force threats, at the same time, you know, the industry is facing a lot of headwinds. You know, a lot of these new basins like the Marcellus or in the Rockies or out in California and in the West and, you know, even in places like Arkansas and Eastern Oklahoma, a lot of these new production basins are also overlapping in really challenging geographies where you have soil issues, you have steep slopes, things like that. And there's this kind of increased awareness in the industry of these geohazard related failures that are occurring. And of course, as a result, pipeline operators are now starting to try to understand, okay, how do we understand what's going on above the pipeline as well as what's going on inside the pipeline? And regulators are aware of this as well. So, you know, there's a lot of new federal requirements that are coming down that are related to earth movement and geotechnical related hazards. And, you know, in addition to that, I think everybody's pretty aware that there's definitely increasing public resistance to pipelines, pipeline hazards, and the risk they pose at the same time. But the good news is that there is technology that is available to go out and identify these things. And you know, want to take a second here to kind of acknowledge that each one of these approaches has its merits. And I'm just going to hide this little guy here while I keep going so I can see the whole slide. So drones are really great. And I think that there's even some other drone presentations at the conference today. You know, they're really great for really, really high resolution data. You know, they can tend to be lower accuracy without the introduction of ground control, but they're really great for small geographies. You know, they don't have really good, you're not going to go fly 1,000-mile or 3,000-mile pipeline in a remote area with a drone, but they're really good for facilities, you know, repeatable data collections, small geographies, things like that. When you introduce fixed wing, you get that kind of geographic scalability that comes into play. So you can start to cover much larger areas. Of course, satellites are really great for higher revisit times. You know, they're revisiting, you know, every couple of days or once a week, things like that. Typically going to be a little bit lower resolution than what you would get from drones or fixed wing aircraft. You have a lot of different sensor types that are out there and that are coming onto market, particularly things like synthetic aperture radar, hyperspectral data, thermal imagery, those types of things. Really, really nice for early warning system. So, give me an idea of where Earth movement may be happening so that I can address it before it becomes an issue. And then you get the LiDAR. And what we found in working with our customers, and we actually started as a drone company, is that, the nature of these threats that they're facing, LiDAR has kind of emerged to us as kind of the most authoritative source of data that you can use. It's an active sensor. It can see through canopy. You can understand what's going on with surface features, but you can also get this really, really clean terrain model at a large geographic scalability that's also really, really accurate and inherently 3D. So what we found is that it's kind of the holy grail for this authoritative data set that's highly accurate, but that also gives you this really, really nice, discrete data that allows you to identify these issues and really do really, really good kind of root cause analysis on them. And, remote sensing and LiDAR isn't new, but traditionally it's had pretty limited adoption because it's traditionally been seen as being very expensive, it's time intensive, it requires a lot of compute power to process, it's fairly niche data, so there's not a ton of people that have the skill sets to unlock the analytics and the decisions that you would be making from it. Really, it's kind of difficult to extract value from. And that's why we've kind of really focused in on LiDAR initially and kind of streamlining the LiDAR value chain. So if you think a little bit about the first bottleneck, acquisition kind of is what it is, right? You're going to have to put a plane in the air. You're going to have to pay pilots. You're going to have to pay for gas. That's probably 60 to 70% of the cost of providing LiDAR. But the first bottleneck in getting value out of that data is processing. So, we kind of view the next 30% or so of the price of LiDAR is in kind of manually processing that data with these desktop workflows and things like that. And so we've really focused on being able to process this data at scale, efficiently, and at a low cost. So I want to talk a little bit about some of the technology at a high level that we use to do that. Anybody that's here that knows me, I have a GIS background, but I'm certainly not a developer or cloud architect. But if you think about the old way of doing things in the cloud, there was this kind of approach that was based around max capacity planning and worst case scenario. Let's go stand up a bunch of servers in the cloud so that we have them available to process data when we need them. We've got the right software on them. We've got, they've got the right amount of storage, the right amount of RAM, all of these things. And that was kind of what you've always had to do in the past. And there's this big shift that is occurring in the industry around kind of dynamic, pre-programmed, desired state ability to spin these things up on demand. So, let's say a new data set comes in, you can dynamically spin up, based on the nature of that data, 1,000 machines or 5,000 machines that already have the right software installed, that already have the right configuration, and you can do all of that highly programmatically. So what's really nice about that is that it gives you the ability to kind of manage your costs for processing this data. So instead of kind of having to have all these servers with high availability, with the right software all the time, you can spin them up when you need them, process data, analyze data, and then kind of shut them off. But you can easily kind of spin them back up when you need to. And another big part of what that enables is this kind of transition from sequential processing to parallelized processing. So, when you dynamically spin up this infrastructure and you can split a single data set into 5,000 or 10,000 pieces on demand, and the machines and software that you need to be able to do that, that really, really streamlines the ability to process this data at speed, at scale, and in a cost-effective way. Also, a lot of this technology that's coming out that enables you to be able to do this gives you the ability to, like, let's say a machine fails or something breaks, something like that, it can automatically and dynamically spin up new machines with the same configuration to replace them. So really, really kind of big shift in data processing dynamics. And by the way, in case anybody here missed it, Esri is starting to embrace this type of model as well. So, the ability to leverage technology like Kubernetes to orchestrate these containers with the software on it, and then microservices that they can call to be able to run a lot of these processing and analytics and things like that. We're not the only ones in the geospatial community that are starting to embrace this kind of new cloud native architecture that's out there. So beyond processing, analytics is a big part of extracting value from this data and relating it back to the problems that you're trying to solve. So we're able to get from kind of raw sensor data into these mechanized models, kind of process data much quicker, much more efficiently, and at a lower cost than a lot of other people are. So we take this data and then we build a terrain model off of it. We build a vegetation model off of it. We build hydrologic models off of it, combine that with publicly available soils data, things like that, and then kind of smash these data sets together in a very academically defensible, statistically defensible way to help our customers identify the most common environmental threats that the industry is facing. So things like geohazards, erosion and inundation, depth of cover, how deep is your pipeline buried? Is it at risk of exposure? Where's third-party activity coming from? New structures that are popping up along the pipeline that might impact your operating pressure, vegetation that's encroaching, and probably most importantly, in addition to all these things, how are these things changing over time? So a lot of, the Earth is a living system, right? Earth is moving, terrain is moving, rain events can drastically impact a lot of these things. So managing and monitoring a lot of these threats, and which are becoming worse, which are getting better, which have been mitigated, and monitoring throughout time is a really, really important component. And then, of course, understanding how all of these things intersect with your infrastructure so that you can understand which are the greatest threat, which need to be mitigated first, which can wait, those types of things. So basically what we do is we go out and we collect base data. So we fly LiDAR, and you have the option to include imagery. We then produce a digital surface model from that accounts for trees and buildings and fences and power lines and things like that. But then you can also strip all of that data away into a really, really high fidelity digital terrain model. And then on top of that, we have written algorithms that can identify geohazards within the terrain. So this is an example where you have a pipeline right of way and you have some geohazards that are intersecting it. So these are actual landslides that start off of right of way and end off of right of way, and that are also under vegetation. So if you were flying over this with an aerial patrol or even walking this right of way, you probably wouldn't even know that there's an active geohazard. But when you strip away all those surface features, get this really, really nice, clean digital terrain model that LiDAR enables you to go out and collect, you can see that there's a really clearly defined scarp slope, a really clearly defined toe slope, and there's an active geohazard here that was hidden underneath the vegetation. In addition to the geohazards themselves, we will then intersect these with our customers' center lines and tell you which is the greatest threat based on, is it upslope of the pipeline? Is it downslope of the pipeline? Is it perpendicular to it? Is it parallel to it? Is it, how large is it? Is the terrain concave? Is it convex? What's the hydrologic energy? We can look at things like the soil type, what's the liquid limit of the soil, the bulk density of the soil, and we can also help predict where landslides are likely to occur in the future based on those underlying variables that we have trained machine learned analytics on. One of the other major contributing factors to these environmental threats is hydrology. So this is a really good example of a slip that is adjacent to a pipeline right-of-way here. And you might look at this and kind of see, okay, I can see a scarp slope, I can see a toe slope, you know, it's kind of downhill, kind of perpendicular type flow to the pipeline. But if you didn't understand the underlying hydrologic condition, you may not really understand how to go out and mitigate this particular issue or why it's such high priority. So we actually have run some analytics in this example that tell us what is the amount of hydrologic energy that's flowing over the surface here that might be contributing to the instability of this slope. And then we actually extract out those discrete flow paths that are likely causing those issues. So, you know, you might go in and need to put a water bar here to mitigate some of this hydrologic energy, things like that. So really, really nice data set for root cause analysis. And like I mentioned earlier, many of these things are changing over time. So this is a pretty cool example of so in the Appalachian region, we typically fly in the fall and in the spring during leaf off conditions, so we can get the best data, LiDAR data available. In this example, you can see a slip on the left and a slip on the right. And by the way, we actually delineate the scarp slope and the toe slope for our customers, so you can see how those things are changing over time as well. And we flew this in the spring, and when we went back and flew it the following fall, you can see that these two actually combine together into one really large slip, and basically this entire hill slope is failing. So you have geohazards that might be, you know, a 3 out of 10 or 4 out of 10 in the spring that have turned into a 10 out of 10 in terms of their threat level in only a matter of 6 months. Of course, depth of cover is also a major issue. If your pipeline is exposed, then it has potential to be ruptured. So understanding where you might have depth of cover issues. So if you have a good Z value for your center line, we can compare that to the terrain to help you, focus your survey efforts where you are likely to have issues versus where you should have pretty good cover. Things like encroachment from new structures that might impact operating pressure, vegetation that's encroaching that needs to be limited or managed, things like that. So some pretty good examples of some of the analytics that we run to relate this data back to the problems our customers are trying to solve. In addition to that, like I was saying earlier, a lot of these data sets, this is a lot of data. If you think about having to go and fly a 300-mile pipeline, depending on, your buffer size, things like that, just for the raw LiDAR, terrain, and DSM, you're looking at about 70 terabytes of data. But to run all the analytics on top of that data that we run to actually solve the problems you're trying to solve and make the decisions you're trying to make, you actually have to produce about 7 times that. So now you've got half a petabyte of data that you need to manage, analyze, distribute throughout your organization to go and support those decisions that are being made. In working with our customers, that's about $400,000 in infrastructure management, so the actual infrastructure to manage the data, software licensing, labor, things like that. And if you look at standards that are out there for how long it takes to process that amount of data, so 3 square miles with traditional desktop workflows takes about 30 hours to process into a usable data set. Working with companies like ours, we basically manage and host and serve all of that data to you, eliminating that entire burden. The same data that takes most LiDAR providers 30 hours to process, we can process in 20 minutes. Then you also need to visualize this data. Because we serve this data to our customers, we don't care. You can use your viewer, your application, like in Portal, ArcGIS, Arc Desktop, AutoCAD, whatever. You can use our 3D web visualization tool to interrogate, interact with a lot of this data. This is really where the decision happens, is when you start looking at these things and interrogating them. And what's really cool about the approach that we've taken is that it's actually enabled us to kind of back into streamlining acquisition. So because we brought a lot of customers together in the Appalachian region, there's a lot of landslides, a lot of pipelines, a lot of upstream activity, things like that. We're actually now taking a content program approach. So this is just a quick map of all the pipelines that are in Appalachia. So typically, if you wanted to go fly LiDAR over this line, you kind of have to follow all the bends and go collect the data, make sure that you have the right overlap, and kind of it's very inefficient to follow these kind of windy spider web systems that are in the region. But we've pulled together so many customers out there that we're actually now able to go out and just kind of fly a lawnmower pattern over the entire region and enable customers to subscribe to data within that region instead of, and there's a major cost sharing element to that. So you're not kind of paying to fly your individual system and taking on the burden of all those inefficiencies. Now we don't fly this entire polygon twice a year, but we do fly about 75% of it. So do it biannual, leaf off, no snow. We're doing about 10,000 square miles twice a year. We've identified about 14,000 geohazards in the region, ranked, prioritized, and monitored twice a year on an annual basis. So a lot of acquisition efficiency we're now able to gain by taking this kind of content program approach. I know we're pretty short on time, but I did want to give you just kind of a quick view of what some of these things look like in action. So this is our 3D web viewer with some sample data sets out in the Eastern Ohio region of Appalachia. And I need to move this. I've got a couple of bookmarks I've saved here so we can go take a look at some of these things. So this is just a quick example of what a geohazard looks like on a terrain model. So you can see scarp slope identified, toe slope down here. If I can kind of drop more into 3D, so you can kind of see that this geohazard is directly intersecting the center line of a pipeline and moving perpendicular, so downhill, pretty scary one here. Then you can turn on the hydrology underneath, and you can start to see that it looks like there's a water bar here that is failing and is likely, there's additional flow that's occurring out on the edge of this geohazard. So really nice way to see some quick root cause analysis. Let's take a look at a couple other examples, and then we can kind of round things out here. Another pretty cool example of a geohazard. Again, you can see that really well-defined scarp slope up here, toe slope at the bottom. You can see the hydrologic influence, almost no stopping of that hydrologic energy, probably contributing to the instability of this slope. And why don't we pick one more analytic to give you a look at here before I come back to the deck, just because of time. So hill slope threat, let me just turn this on. So we've also are able to predict where landslides are likely to occur based on hydrologic energy, connectivity to the pipeline, things like that. So you can see, higher red means higher likelihood of incidents. The steeper the slope, the more concave it is, the soil type, hydrologic energy, things like that. So just kind of a quick look at a hill slope threat assessment. So wanted to share a real quick customer success story out in the region and how our customers are using these types of analytics to save money, reduce risk, things like that. So based on working with our customers, the average cost in the region to reactively repair a geohazard and get it from looking like this to looking like that, if it's already gotten bad and kind of gotten out of control and is a major threat to your system, the average price is anywhere from $600,000 to $1 million, depending on its size, location, how hard it is to get to, things like that. But if you can get ahead of these things and fix them before they become an issue, your costs are, a third to a fifth of that. So this particular customer that we worked with had 250 or so slips on their system that were just completely unprioritized. They were just kind of fixing whatever they could get to. They were very, very reactive. Of course, reactive repairs are much more expensive than proactive repairs. They were experiencing 3 to 5 shut-ins a year. So they would have to shut down the pipeline, fix these things, and then turn it back on. And every time they had a shut-in, it was $7 million a day in lost revenue that they weren't recognizing when that pipeline was shut down. So they worked with us to identify and prioritize these things. First of all, we found 12 slips that they were completely unaware of, but they worked with us to prioritize these things and figure out which were the greatest threat, which should be fixed first, because they were worse. And we were actually able to help them reduce their budget from $20 million a year to $8 million a year by prioritizing what was the greatest threat. They now experience 0 shut-ins a year and have recovered $150 million a year in revenue from not having to shut their pipeline down anymore. So pretty cool example of some real customer success. So with that, I think I'm kind of right at time here. Just wanted to, before we go into questions, just wanted to kind of talk a little bit about how we work with our customers. The approach we take is, what are the decisions you're trying to make? What data, we'll then work with you to understand what are the data types that are available to help, what analytics are required on top of that data to relate it to the decision you're trying to make. Are those decisions repeatable? Can those analytics be automated? And of course, can they become smarter, more accurate, better over time with AI or machine learning? So, this was our pipeline example in the Appalachian region. We work with upstream customers to automate site selection for pad sites or to mitigate stormwater. We work all over the country in areas with steep slopes and where inundation and flood and river scouring and things like that are an issue. But thought I'd maybe just kind of leave it there. And if anybody has any questions, I'm happy to take them now.